Welcome back everyone. In this lecture we will continue to study the basis of a root system, and we saw the existence of bases in the last class. So in this class actually I will prove that the bases will arise as pi of gammas for some gamma regular. Okay, let's recall what we have done before, and then I will continue with the result. So recall, we define what is called this Weyl chambers, which are connected components of this E difference union P alpha alpha in phi. So we looked at this union P alpha alpha in phi, and then the complement of that, which we called this E minus union P alpha alpha and phi. Then we realize this can be written as union of connected components. So this is union of connected components, and those connected components we called Weyl chambers. Okay. So then what we realized, so if we take some gamma inside this complement, which we call it regular element. Okay. So let gamma is being element of V, which is not in this union of P alpha alpha in phi. So that means this is a regular element. So then we saw that this gamma is indeed separates this pi into two disjoint sets. One is pi plus of gamma, which is those beta in phi such that beta of gamma is positive, and then you have this phi minus of gamma, which is just minus of phi plus of gamma. So then we saw that minus phi plus of gamma and phi plus of gamma is going to be exactly phi, and you have this pi of gamma, which is subset of phi plus of gamma consisting of indecomposable elements. From this phi plus of gamma, and we saw that this form a base of phi. So this is what we proved so far. So now what we want to do, we want to prove that all the bases of this phi arises in this way only. That means, so given a base, so let pi be a base of phi. So then there exists gamma, which is regular from E minus union P alpha alpha in phi, such that this pi of gamma is going to be exactly pi. So this is the theorem that we want to prove. Okay. So this proves that the set of all bases, the set of all bases of phi are nothing but just pi of gamma, where gamma runs over all these regular elements. Note that, so there are only finitely many bases are possible because pi itself is finite. So that means there are lots of identification that happens between pi gamma. So pi gamma will be equal to pi gamma dash for many elements. We will determine later when this happens. Okay, so how one actually approaches this? So for this purpose, first let us use the definition of pi. So pi is being a base, so that actually tells us that pi first of all must be basis. So once we give basis, then we can actually take intersection of this positive open half spaces associated with the basis, and we can see that this intersection must be non-avoid. So what I mean by that? So let's look at these elements of pi. Let's label them. Okay. So let's say you have pi. So which you label them as alpha 1 etc. alpha L, where L is the rank of phi, which is dimension of phi. Okay. So, now once you have these elements alpha 1 etcetera alpha L. So, now you can define this positive open of spaces associated with this space. Okay. What is that? So, you take some subset of E, so which is collection of all x such that x comma alpha I is positive for all I 1 to L. So, this is the intersection of, so this is the intersection of all these positive open of spaces associated with elements of pi. Okay. So, our claim is actually this is non-empty. So, we claim that, so this must be non-empty. So, this is actually can be proved easily. Okay, I will just sketch a proof, I will leave it to you to check. So, check that if we take delta I be the projection of this alpha I on the orthogonal complement of the subspace spanned by all basis vectors except alpha I. So, then you can take, okay, what is delta I? So, this is the projection, okay. You take the projection of alpha I, where on the orthogonal complement, on the orthogonal complement of the subspace spanned by all basis elements except alpha I, that means all alpha j where j is not equal to I. So, then you can consider this gamma which is summation some R I delta I where I range from 1 to L where R I is positive. So, then you can prove that this gamma must be there inside this intersection. Okay. So, let me call it capital A. So, this must be inside this capital A. You can directly compute this gamma comma alpha I, and then you can see that what happens. Okay. Let's do it now. So, let us say gamma alpha I. So, that is going to be exactly equal to summation R I delta, okay, R j delta j alpha I, and then where j range from 1 to L. Now, since this delta I is the projection of alpha I on the orthogonal complement of the subspace spanned by this. So, that means this delta I will be orthogonal to alpha j for all j not equal to I. So, that means the only thing that lives here is summation actually all this delta j alpha I will be 0. So, then what do you get exactly equal to R I delta I alpha I. Since delta I is the projection of alpha I on the orthogonal complement, you can see that this must be non-zero and this is also must be positive. So, that forces that this gamma of alpha I is positive for all I range from 1 to n. So, this is simple construction that tells us that this intersection of this positive open of spaces associated with any basis must be non-empty. But geometrically you can see that all these positive off spaces they will have actually measure infinite. Okay. If we take this finitely many of them and then intersect, you will still have measure infinite open subset. Okay. This is going to be open subset and this will be convex open subset, that is not hard to see. So, now how one uses this? So, now you can go back to our pi, okay, that pi that we have inside phi. So, then you can use this earlier observation and then choose gamma inside E such that this gamma of alpha is actually positive for all alpha in pi. So, this can be done using our earlier observation. So, now you can see that since phi is actually pi is a base inside phi, you can see that this gamma must be regular, okay, using B 2 and pi is base, we get gamma is regular. So, what is the meaning of that? That means gamma comma beta is non-zero for all beta inside phi. Okay. So, now since gamma is regular, one can actually define what is called phi plus of gamma, that is those beta in phi such that beta gamma is positive. Now, you can see that pi by definition satisfies this gamma alpha positive for all alpha in pi. So, that implies pi is sits inside phi plus of gamma, and note that phi plus is with respect to pi, all these elements of phi plus will be non-negative integral linear combination of elements of pi. So, that forces that this pi sits inside phi plus and this phi plus sits inside phi plus of gamma, and this also again forces that phi minus sits inside phi minus of gamma, which is minus phi plus of gamma. So, that implies that using the cardinality argument, you can see that phi plus must be exactly equal to phi plus of gamma, as phi plus is just going to be the cardinality of phi plus is going to be cardinality of phi divided by 2, which is same as cardinality of phi plus of gamma. Okay. So, that forces that this phi plus must be equal to phi plus of gamma. So, now since pi sits inside this phi plus, which is equal to phi plus of gamma, so you can see that this pi is naturally elements of pi of gamma. Now, since the cardinality of pi is same as cardinality of pi of gamma, as both of them are bases. So, both of them are basis of capital E. So, you can conclude that pi must be equal to pi of gamma. Okay. So, this actually tells us that if we start with pi, which is a base, so then there exists gamma regular such that pi of gamma equal to pi. So, that means all the elements of bases must come from this pi of gamma for some gamma regular. So, this is kind of motivates us to understand what happens if you vary gamma over this set E difference union P alpha. So, let us try to understand that. Okay. But before that, let us make some observations about the connection between the simple roots and the positive roots it generates. Okay. So, you start with pi, which is sitting inside, let us say phi. So, then we just observe that pi must be equal to pi of gamma for some gamma which is regular, which is in E difference union P alpha alpha in phi. So, then what we observed? We also observed that there is this phi plus of gamma. So, that one can define. So, that is going to be exactly phi plus. So, now it is easy to see, okay, it is easy to see that pi equal to or pi of gamma equal to pi of gamma dash if and only if this phi plus of gamma must be equal to phi plus of gamma dash. So, this is not hard to see. Okay. So, in particularly you can also see that in this case this this gamma and gamma dash. So, they both lie on the same side of the hyperplanes P alpha. So, this is happens if and only if gamma and gamma dash lie on the same side of each hyperplane P alpha alpha in phi, and this happens if and only if this chamber that is defined by gamma must be same as the chamber defined by gamma dash. So, that means if gamma and gamma dash, if they come from same Weyl chambers, okay, so then the corresponding pi of gamma dash must be same, and as well as this phi plus of gamma and phi plus of gamma dash must be same. Since there are only finitely many of them, you can see that there are only finitely many of these Weyl chambers. So, if we fix some base, then the chamber that is corresponding to that fixed base will be called fundamental Weyl chamber. Okay. We fix a base pi of phi. So, then we know that, so there is this chamber that actually corresponds to pi. So, in particularly pi will be pi of gamma, and then you have this chamber corresponding to this gamma. So, which we just define to be so this we take it to be the chamber corresponding to pi, and this we call it fundamental chamber. So, that means we are working with one fixed base now. Okay. This is, we call it fundamental chamber. Okay. So, what we have done now, so we have actually made connection between this set of all bases. So, set of all bases that you take of phi, and then from this we have natural way to go from the set of all positive roots of this phi, and then from here we can go to the set of all chambers of E, okay, Weyl chambers. So, note that once phi plus is given, okay, so then it must contain a unique base in it. Okay. So, this correspondence is actually one to one correspondence. So, going from a base to its positive roots. Okay. So, this is a one to one. Similarly, going from this positive roots to the chamber, so that is also is actually a one to one correspondence. Okay. So, we will see like if this is phi plus of gamma, so then naturally we are sending this to C of gamma, so which is we denote it by C of pi. So, this is also a one to one correspondence. So, these are all something we already checked implicitly. So, I just leave it to you to check very explicitly. So, this statement you check. So, now you can see that there is a Weyl group acting on capital E, and this Weyl group will naturally act on the set of all Weyl chambers, because the Weyl group is naturally acting on this p alphas. Okay. So, you can see that the Weyl group W acts on this union p alpha in phi, because the Weyl group acts on this capital phi, and in particularly it acts on all the hyperplanes perpendicular to roots of phi. Okay. So, that forces that this Weyl group naturally acts on this complement E minus union p alpha in phi. Okay. Because this is W invariant, so its complement is also W invariant. Since W actually isometry on each element of W acts as isometry element on E, so that says that the connected components of this E minus union p alpha should be mapped to connected component. So, in particularly W acts on the set of Weyl chambers, the set of Weyl chambers. So, not only that, you can see that easily, if pi is a base, then if you take W in W, then W pi also must be a base. So, this is some easy exercise, I will leave it. So, if W in W and pi is a base of phi, so then W of pi, that also must be a base of phi. So, that means W acts on the set of bases. So, W acts on the set of bases. So, now it is not hard to see the way the W acts on this Weyl chamber. Suppose if you take the Weyl chamber to be C gamma and then W is in W, then the W naturally maps this C gamma to just C of W gamma. So, this is something very easy to check. It is enough to check it for reflections. For reflection, this is just obvious because W is just isometry. Okay. If gamma some x is positive, then you can see that W gamma W x is also positive. Okay. So, here C gamma is actually is those elements gamma such that so they all lie in the one side of the each hyperplane. So, you can see that there is a way to actually define C gamma. So, this is something I will leave it you to check. So, here the exercise. So, C gamma is also has this other way of expressing. So, you collect those gamma dash inside E such that gamma gamma dash both lie on the same side of the each hyperplane P alpha, okay, for all alpha in phi. But if you take element that is coming from phi plus of gamma, you can see that gamma alpha must be positive. So, that means gamma and gamma dash must be on the positive side of this P alpha, where alpha coming from phi plus of gamma. So, that actually gives another definition of C gamma. So, this is those gamma dash in E such that gamma dash alpha must be positive for all alpha coming from phi plus of gamma. So, this is one defined. So, because phi plus of gamma is uniquely determined by gamma. So, you can call it phi plus. So, that phi plus actually defines what is this C gamma. Okay. From this you can see that if you apply W on C gamma, then you get C W gamma. So, that is also not hard to prove. So, now we also seen that if pi is pi of gamma, so then if you apply W on pi, then what happens, you can see that W of pi of gamma. So, because that is inside again it is a base and it is not hard to see using the action of this W on this Weyl chambers. Okay, this maybe I will leave it as exercise. Again, if you think about the definition, so then you get, so W of pi will be equal to W of pi of gamma if pi equal to pi of gamma. Okay. So, then you can see that this must be exactly equal to pi of W of gamma, as W of C gamma is same as C of W gamma. Okay. So, that proves that W of pi of gamma is exactly equal to pi of W gamma. So, this is the way W is going to act on all this set of bases. Okay. Similarly, one can actually get the action on the phi plus gamma. So, on phi plus gamma also it is going to be W of phi plus of gamma will be exactly phi plus of W gamma. So, this is how W is going to act on the set of positive roots. So, that means, so the one to one correspondence that you have among all these sets, so these one to one correspondence respects the action of W. So, this one to one correspondence respects the action of W on each set. Okay. So, this is very important observation. Now, let us actually use these observations and then actually get more information about the set of positive roots and so on. So, ultimately what we want to prove, we will prove that the action that we have on the set of bases, so that will be actually simply transitive action. Okay. In particularly this W acting on this Weyl chambers, again it will be simply transitive action. So, in particularly we can actually talk about the fundamental domain for the action of W inside E. So, that can be identified with this C of pi bar. Okay. So, that is our ultimate goal. So, what are all our goals? Let me write it so that we will not be lost. So, the very first goal, so that W acts on the set of bases or equivalently the set of Weyl chambers in a simply transitive fashion. So, that means if we take any two bases, so that must be W conjugate. So, very explicitly if delta, let me call it pi and pi dash both are bases of phi. So, then there exists W and this W is actually unique W in W such that W pi must be equal to pi dash. Okay. So, this is what simply transitive action, and the second goal we will see that. So, we can talk about the fundamental domain for the action of W on V. So, we will prove that this C of pi bar. So, this is the fundamental domain. So, this is the fundamental domain for the action of W on capital E. Again, what is the meaning of that? So, that means, so if you look at the union of W conjugates of this set, that must be exactly E. So, E must be union of W conjugates of this set C of pi bar, where W in W, and if we take sigma lambda equal to mu for some sigma in W, then in particularly like so this conjugation must be unique. So, in a way, if sigma lambda equal to lambda for some lambda in this C pi bar and sigma in W, then that should give us sigma to be identity on E. Okay. So, this is the meaning of this is the fundamental domain for the action of W on E. Okay, let's do these things slowly. So, these are all our goals now. So, to prove that W actually permutes the basis of phi, we need to actually prove the following. Okay. So, we will indeed work with some smaller group and then later we will prove that that smaller group is indeed entire W. So, what is that smaller group? Again, that is also maybe one can put it in the goal. So, we will prove that this W is indeed generated by reflections corresponding to the base pi. Okay. We already know by definition W is subgroup of GL of E generated by all reflections corresponding to roots of roots, that is elements of phi, but this pi is actually a smaller subset. Already you can divide, okay, because pi is equal to pi plus of gamma disjoint union minus pi plus of gamma. You can see that W is actually given by subgroup generated by S alpha, alpha coming from phi plus of gamma. So, this is easy, but we will prove that in very strong statement that W is indeed generated by what is called the simple reflections. So, these are called simple reflection because these are all reflections corresponding to the simple roots alpha. So, this is something very strong condition that we make. Okay. So, indeed we prove that if we take W dash to be this subgroup, then that subgroup indeed acts on this set of bases simply transitively. So, that is going to help us to prove indeed this subgroup is exactly equal to W. Okay, let us prove this. So, here is the theorem. So, we fix bases. So, let pi be a base of V. Okay. So, then what we want to prove? We want to prove that if you take any other base, so then that must be W conjugate to this pi. But we know that any other base will be just pi of gamma for some gamma regular. So, then given that pi of gamma, if we prove that pi of W gamma is just this pi, then we are done. Okay. So, our so let's prove this. So, here is the first statement. If gamma is E and gamma is regular, so we want to prove there exists some W in W such that this W gamma inner product with alpha. So, this is going to be positive for all alpha in pi. Okay. So, that means what? That means, so this W is fixed. Okay. So, this W gamma, let us call it gamma dash. Okay. Then gamma dash alpha is positive for alpha in pi. So, this says, so this implies immediately that pi of W gamma is nothing but just pi, because this pi is uniquely determined by this thing. Okay. So, if we go back to the definition of this pi, so pi will be exactly equal to some pi of gamma dash. Okay. But what is that gamma dash? That gamma dash is chosen to be gamma dash such that the inner product gamma dash alpha must be positive for all alpha in pi. Okay. So, now from that you can conclude that pi of W of gamma must be equal to this pi of gamma dash, which is pi. Okay. So, in particularly the Weyl group acts transitively on the Weyl chambers. So, this implies the Weyl group acts transitively on Weyl chambers. So, that is again on the basis. Okay. Okay. So, what is the second statement? Again it is it says the same thing. Okay. So, if we take pi dash to be another base, so then there exists W such that pi dash W of pi dash will be exactly pi. Okay. From this we can conclude. So, that is the second statement. So, given pi dash, so which is exactly pi of gamma, there exists W in W such that W of pi of gamma is exactly pi. The third statement, if alpha is just a root, so then you can prove that there exists W in W such that W of alpha is going to be element of your pi. So, that means each element of pi is conjugate to some simple root. The fourth statement, it says W is indeed generated by S alphas, alpha coming from pi. The fifth statement, it says if some W fixes pi for some W in W, then we must have W equal to identity on E. So, this says W acts simply transitively on the set of bases. Okay. So, to prove this, what we do, we just take this W dash, which is the subgroup of W generated by all the simple reflections. So, right now we do not know whether it is equal to W or not, but later we will deduce that it must be equal to W. So, for the first statement, you can see that if we take this set of positive roots, okay, so that will be actually given by so here is the small exercise that is aside. So, if we take these positive roots that are defined by this pi. So, this is the positive roots, okay, defined by pi. So, then one can prove that if we take this alpha in pi. So, then S alpha pi plus difference alpha. So, this should be exactly equal to pi plus difference alpha. So, that means this S alpha actually permutes all the positive roots other than alpha. So, indeed we know that S alpha of alpha will be minus alpha. So, that means this S alpha sends alpha to its negative. So, that means it cannot be like part of this. So, if you remove that alpha from positive roots, then you can conclude that this S alpha just permutes all the positive roots. So, now what we do, we just write delta to be this off sum of positive roots, where alpha coming from phi plus. Okay. So, then what we can do, we can actually choose sigma that is coming from W dash such that this sigma gamma delta that must be as big as possible. Okay. So, choose sigma coming from W dash. So, such that the sigma gamma comma delta. So, that is maximum possible. Okay. This is as big as possible. Okay. So, how one can choose that, because W dash is being a finite subgroup of W. So, one can just look at all this sigma gamma delta. Okay. So, since this gamma is regular, so you can see that this sigma gamma delta. So, that must be so let us calculate and see what happens. So, sigma of gamma delta. So, that is going to be exactly equal to gamma times sigma delta. Okay. This gamma is being regular. You can see that. Okay. So, it does not matter whether it is 0 or non 0, but since when sigma runs over W dash, the sigma gamma will be only finitely many. So, then you can compute this inner product sigma gamma delta, and then you can choose maximum possible, there is no issue. Okay. So, that is fine. So, now let us look at this alpha simple root. So, then for alpha in pi, you can see that this S alpha must be in W dash. So, in particularly S alpha sigma, that should be inside W dash. Okay. So, now for the choice of sigma, what happens? So, the sigma gamma delta. So, this is going to be bigger than sigma S alpha sigma times sigma of gamma times delta. So, that is going to be smaller than this. Okay. Sigma gamma delta must be greater than or equal to S alpha sigma gamma gamma delta. So, let us compute this, then we get sigma of gamma delta greater than or equal to sigma of gamma S alpha of delta, but S alpha of delta what it is, since delta is off sum of alpha where alpha positive. So, then S alpha of delta will be exactly equal to off sum of summation alpha, sorry, let us call it beta because S alpha we are applying. So, let us take this to be beta. So, this is beta, beta positive, beta where beta not equal to alpha, beta positive plus of alpha we can take. So, now you can see that S alpha of delta is going to be exactly equal to, so this part of the sum will be preserved by S alpha because S alpha permutes all the positive roots except alpha. So, then that implies that this sum must be permuted among themselves. So, then you get exactly of summation beta, beta not equal to alpha, beta positive. But what happens to this? This is going to be minus alpha by 2. So, this is going to be minus alpha by 2. So, then now you can add 1 alpha by 2 and then subtract 1 alpha by 2. So, then you can see that this plus this going to give us delta and then delta minus alpha. So, that means S alpha of delta is exactly delta minus alpha. So, that implies that sigma gamma delta is greater than or equal to sigma gamma comma delta minus alpha. So, now if you just calculate, so this implies that sigma gamma alpha must be greater than or equal to 0. Since gamma is regular and sigma permutes all the roots, so that implies that sigma gamma comma alpha, so that must be positive. So, this is what we are getting, and this is actually true for any alpha positive. So, that is what we proved. So, this proves that the sigma gamma alpha is actually positive for all alpha from pi. But that means what? That means the sigma gamma which is gamma dash. So, this is going to be a regular element, and if you think about it, if then this forces that this pi equal to pi of gamma dash. So, that is how the gamma dash is defined, okay, because this is what uniquely defines that gamma dash that corresponds to pi. So, this means this sigma sends this C of gamma to this C of pi. Okay. In particularly, if you think about it, then the sigma actually sends this pi of gamma to pi. Okay. So, that is what happens. So, that means any two bases they are conjugate under this subgroup W dash. So, in particularly W dash permutes all the Weyl chambers and it also permutes all the bases. So, now if you want to prove that any root is actually W conjugate to some simple root. So, from this second part you can see that any two bases are conjugate. So, that implies that if given a root is part of a base, then we are done. Okay. So, let us prove C. So, to what is C? If alpha is a root, so then we want to prove that there exists W in W such that W of alpha is actually again inside pi. So, there are actually many ways to prove this result. So, let me give at least two proofs. So, one proof just uses induction, okay, induction on the height of alpha. So, what we can do, given alpha in phi, you can write that alpha as some integral linear combination of elements from pi, either with non-negative coefficients or non-positive coefficients. So, now given this alpha, so if you write summation k beta beta, where beta is coming from pi. So, you know that these k betas are either non-negative integers or non-positive integers. So, then you can define what is called this height of alpha with respect to pi. So, that is going to be just sum of all these k betas coming from pi. Now, by inducting on this height, you can prove this result. So, let us prove this by induction. Okay. So, maybe I will leave it to you to prove this. This is simple. Okay. So, use induction on this height of alpha and prove that there exists W1 W dash such that W of alpha is in pi. Okay. So, this is something easy, not that hard. So, let us now prove that in other way the same result. So, in order to prove this alpha indeed W conjugate to some simple root, what we are going to do? We are going to say that this alpha is indeed part of some basis. So, what is our claim? Claim is alpha is inside some delta of some pi of gamma dash for some gamma dash which is regular. Okay. Okay. So, how one can do this? So, for that purpose let us look at the hyperplanes, okay, p beta. So, they are all actually distinct from p alpha when beta is actually runs over elements of pi. Okay. So, what we do, we indeed take this alpha. So, the only roots that are proportional to alpha are plus or minus alpha. So, in particularly this p beta, okay, when beta is not equal to plus or minus alpha. So, these are all, okay, these planes are all distinct from p alpha. Okay. So, in particularly this p alpha cannot be written as okay, or p alpha cannot lie inside this union p beta where beta is not equal to plus or minus alpha. So, if it is the case, then what happens? Then p alpha can be written as union of p alpha intersection p beta, but note that p alpha intersection p beta, it will have dimension 1 less than dimension of p alpha. So, that forces that p alpha can be written as union of finitely many proper subspaces. So, that is observed. So, that is why this p alpha cannot be contained in union p beta where p beta not equal to alpha. So, then what one can do? One can choose this gamma dash inside your Weyl chamber. So, that is actually let us say closer to this hyperplane p alpha. So, you have this hyperplane, so which is p alpha. Okay. So, this gamma which is regular element, gamma dash which is regular element. So, that is closer to this p alpha, but it actually kind of stays away far from other hyperplanes, because all other hyperplanes there are only finitely many. So, because there are only finitely many hyperplanes which are like there inside this E. So, you can see that one can talk about distance between these two hyperplanes. Okay. So, given p alpha p beta, one can talk about kind of so distance means distance with respect to let us say the inner product. So, what I want to claim, so okay, maybe you can check yourself. So, this is not that hard. So, you can choose this gamma such that which is close enough to you can choose gamma dash that is close enough to gamma. So, gamma is also regular element. Okay. So, which is already taken to be gamma, we will just fix gamma which is inside your p alpha, but gamma is not in p beta for all beta not equal to plus or minus. So, that means this gamma is somewhere here. So, with respect to this gamma, so we choose this gamma dash that is close to this gamma. Okay. So, this is close enough to gamma. So, that if you take inner product with gamma dash comma alpha, so that is some epsilon which is positive. So, this gamma dash is not lying on the hyperplane, it is lying on the positive side of the hyperplane. So, while if you compute this gamma dash with beta, okay, the absolute value of that is bigger than epsilon. Okay. So, this is somewhat closer to gamma. So, now with respect to gamma you can actually look at all possible gamma dash comma gamma. So, that inner product you can look at. So, this R alpha will be just line that is perpendicular to this hyperplane. So, now using this information you can choose this gamma dash that satisfies these two properties. So, then evidently you can see that this alpha must lie inside pi of gamma dash, because alpha must be indecomposable. So, because if it is written as sum of some beta 1 plus beta 2, you can see that then gamma dash of alpha will be exactly equal to gamma dash comma beta 1 plus gamma dash comma beta 2. Now, since this beta 1 beta 2 if they are coming from positive side, so beta 1 comma gamma dash is positive and beta 2 gamma dash that is also positive, then that forces that these two are actually bigger than epsilon and bigger than epsilon, then this should be bigger than 2 epsilon, but that is not the case. We have chosen so that gamma dash comma alpha is exactly epsilon. So, that forces this alpha to be indecomposable element. So, that means alpha must be inside your pi of gamma dash. So, since there exists W in W such that W of pi of gamma dash is exactly pi, that forces that this W alpha is exactly in pi. So, this proves that any root of phi must be W conjugate to some simple root. Okay. So, now we are ready to actually prove W dash is exactly W. So, for that purpose let us start with some alpha inside phi. So, now we know that there exists W in W such that W of alpha inside pi. So, now you can see that let us call this is beta. So, then this S beta is exactly equal to W S alpha W inverse, because W S alpha W inverse is given by W of S of W of alpha. So, this proves that this W inverse S beta W which is exactly S alpha. So, this is going to be inside your W dash, because this W is coming from W dash. Okay. Since S beta is also coming from, as W dash is W is coming from W dash, and S beta is again coming from W dash, that forces that S alpha is inside W dash. So, since W is generated by S alpha, alpha is in phi, you can see that this is subset of W dash, that proves W equal to W dash. So, this indeed proves W is actually generated by all the simple reflection that comes from this pi. So, now what is the last statement? It is about the simply transitive action. So, that is E. So, if W of pi is same as pi, so then we claim that W must be identity on E. So, how one can prove this? So, since this W is actually comes from W, capital W, which is exactly equal to W dash. So, then you can see that W can be written as product of simple reflections, and then we take it to be product of simple reflection in a minimal way possible. Okay, let us write S alpha of 1 etcetera S alpha t, where this S alpha i's they are all simple reflections and this t is minimum possible. Okay. So, then you can see that. Okay. So, this is something easy exercise, maybe I will do it in the next class. So, one can check easily that if you take w of alpha t, so then that must be negative. Okay. So, but w of pi is equal to pi. So, that means w of alpha t must be positive, because this is again inside pi. So, which actually gives us contradiction. So, that forces that this t must be 0. So, that forces that this w must be identity on. So, this proves that w acts on this set of bases by simply transitively. Okay, I will stop here. So, the results that I actually assumed, which is two results. So, one is S alpha permutes all the positive roots except alpha, and whenever you write w as product of this simple reflection such that t minimal, then w of alpha t is negative. So, those results I will prove in next class. Okay, thanks. I will stop here.